Alright, so we're back again. It's Niaki. It's Niaki Osteozone. So today we're going to have another discussion for chemistry, A-level chemistry from the Cambridge exam board. So this is multiple choice paper 1-1 of the October-November 2023 session. So if you're doing Cambridge, you need to take note of these instructions. And also if you're not doing Cambridge, you need only to stick to data, because chemistry still remains the same regardless of your exam board. So we are now diving on to the first part, the multiple choice paper. So number 1 says sodium azide with this formula is an explosive used in inflict airbags in cars when there is a crash. So it consists of positive sodium ions and the azide ion. What are the number of electrons in the sodium ions and the number of electrons in the azide ion? So for multiple choice, we mainly use the method of elimination, trying to find the most appropriate answer, because some of the answers may sound to be true, but we need to carry a forensic analysis so that we are going to be left with the correct answer. So we've got the formula sodium azide. So this is the formula. So we are going to derive the ions. So this is the sodium ion, and then this one is the azide ion. So the charge of the azide ion is equal to 1, the coefficient of the charge, since we have 1 atom of sodium here, and the charge also for sodium is equal to 1, since we have 1 azide ion here. So this one is equal to -1, and this one is equal to positive 1. So sodium is on number 11 on the periodic table, so meaning to say it has got this electronic configuration 2881. For junior chemistry, this is the electronic configuration, and then we are going to lose this electron from the outermost shell, and we are going to be left with 8. So we are going to have 10 electrons for sodium, and then we are going to eliminate number C, D, and we are left with A and B. And then for azide ion, we have this 3 nitrogen atom and this extra electron from the system. So nitrogen is on number 7 on the periodic table, and then we multiply by 3 atoms. So the number of protons is equal to the number of electrons. So we are going to have 21, and then plus this electron, the negative charge. So we are going to have 22 electrons, right? 3 electrons, 3 nitrogen atoms multiplied by the number of electrons multiplied. We're going to add this one to make it 22. So our answer will become B. And then we are moving on to the next part. The graph shows the variation of the first ionization energy with proton number of some elements. Ionization energy defined as the minimum amount of energy required to remove 1 mole of electron from a gaseous atom to form 1 mole of a gaseous unipositive ion. So you should take note of this definition, because it is often examined in your exams, right? And then the letters are not the actual symbols on the periodic table. And then we've got this graph, ionization energy against proton number. And then the answer says, which statement about the elements is correct? Which statement about the elements is correct? So we have P and X are in the same period. So P and X, where is our P? Here is our P, and then here is our X. So this is false. This is very false, because we have another shell here. This is another shell, and then this is another shell. So P and X can't be in the same shell. So this one is false. And then number B says the general increase from Q, where is our Q? From Q to X is due to increase in atomic radii. So atomic radii decreases across the period, and then nuclear charge increases with increase in proton number. So this one becomes false. And then the next statement says the small decrease from R to S is due to decrease in shielding. So shielding effect in a period is constant. So shielding is relatively constant. So this one becomes false. So the decrease from R to S, so R, so let us say we are in period 3. So period 3, Q is equal to sodium, and then R is equal to magnesium, and then S is equal to aluminium. So this trend is also in period 2 and etc., right? So The electronic configuration for magnesium with 12 electrons is 1s2, 2s2, 2p6, and then 3s2. So this is the electronic configuration of magnesium. And then that one of aluminium is 1s2, 2s2, 2p6, and then 3s2, and then 3p1. So electrons to be removed in aluminium is being removed in the outer orbital, which is relatively far away from the nucleus, experiencing lesser nuclear charge, whereas the electron to be removed in magnesium is closer within the inner shell, which is 3s orbital, which is closer to the nucleus. So this electron experience larger effective nuclear charge compared to this one. That's why we have R having a higher ionization energy compared to S. So this is anomaly associated with period 3 elements. We also have another anomaly here. So this one we can take nitrogen and oxygen. So in nitrogen is on number 7 of the periodic table, meaning to say we've got this electronic configuration 1s2, 2s2, and then 2p3, right? And then for oxygen is on number 8. We're having 1s2, and then 2s2, and then 2p4. So if we were to draw the structure of the p orbitals, this one is for the last orbital for nitrogen, and then this one is for oxygen, right? So as you can see that electrons in oxygen are being removed. The first electron is being removed from a paired orbital. So the electrons are negatively charged. So there is mutual repulsion in this orbital. So meaning to say less energy is required to remove this electron. Why? Because it is already being repelled from this orbital. So that's why we have this V at a lower ionization energy compared to U. In U, electrons is being removed from a stable orbital, right? So there are no mutual repulsions here, whereas here we have got mutual repulsions. And we're now moving on to number D. So number D says the small decrease from U to V is due to repulsion between the paired electrons. So this one is true, as I've illustrated. So as you can see here, we don't mainly focus on the given question, but we try to explain other related concepts within that given radius so that we can broaden our foundation, right? So we are now moving on to number 3. Number 3 says aluminium carbide reacts with aqueous sodium hydroxide, and the two products of the reaction are sodium aluminate and the hydrocarbon, and water molecules are also involved as reactants. So what is the formula of the hydrocarbon? So we are told that water is a reactant. So whenever aluminium carbide reacts with water, we are going to form methane, right? So this is the hydrocarbon we are going to form. So they react according to this equation. So it's aluminium carbide plus sodium hydroxide plus water. We are told water is also a reactant. So we are going to have sodium aluminate plus a hydrocarbon, which is methane, right? So to balance this equation, we are going to have a 4 here and a 4 and a 4 here, right? And then to have a 4 here and a 3 and a 3 here, right? So this equation is now balanced. So our answer here is equal to A. And then number 4 says a sample of 35.6 grams of hydrated sodium carbonate contains 25.84% of sodium ions by mass. When the sample is heated, anhydrous sodium carbonate and water are formed. Which mass of water is given off? So we are required to calculate the mass of water given off. So the mass of the hydrated sodium carbonate, the formula is equal to X moles of. So water of crystallization shows the amount of water bonded to 1 mole of salt in the lattice structure. So here we are told that we are going to have 25%, which is 25.84 over 100 multiplied by the percentage by the mass of the whole sample. So this is the mass of the sodium ions. So we are going to have, going straight to our calculator, so it's going to be 25,84 over 100 multiplied by 35.6. We're going to get 9.19904 grams of the sodium ions. And then we're going to calculate the number or the mass, the number of moles using this mass. So we're going to use this formula, N is equal to mass over MR. So the MR of sodium is equal to 23. So we divide by 23. And we're going to have 0.39995826 moles, right? So this is the number of moles for the sodium. So in sodium carbonate, we are having 2 moles of sodium. So one for every 1 mole of sodium carbonate. So for every 1 mole of sodium carbonate, we are having 2 moles of sodium. So 1 is equal to 2. What about 0.399 and etc. This number, right? So we're going to have less. So we're going to divide this one by 2, right? So we divide by 2. So we're going to get 1.0.1997913 moles of sodium carbonate. And then we go straight to this formula again to calculate the mass of sodium carbonate. So mass is equal to number of moles multiplied by MR. So number of moles is this one, and then the MR, we are simply adding the relative atomic masses of each atom in this compound. So it's 23 by 2 plus 12 plus 16 by 3. So this one will give us 106, right? So we're going to multiply this number of moles by 106, the AR. So by 106 to give us the mass. So by 106. So we are going to have 21.1977 grams as the mass of sodium carbonate. So we subtract the mass of sodium carbonate from this mass of the hydrated sample to find the mass of water. So we're going to say 35.6 minus this mass, and we're going to have 14.4 grams. So our answer is equal to C. And I'm sure it's very, very clear. First we find the number of moles, the percentage by mass of sodium ions, and then we are going to find the number of moles using this formula. And then for every 1 mole of sodium carbonate, we are having 2 moles of sodium ion. We are going to use this ratio, and then we find the number of moles of sodium carbonate, and then calculate mass using this formula again. Mass is equal to number of moles multiplied by MR, and then we are going to have the number of the mass and subtract the mass of sodium carbonate from this mass of the hydrated sample, right? So we are going to have our answer is C. And then we are now moving on to number 5. So number 5 says solid aluminium chloride sublimes at 178 degrees Celsius. Which structure best represents the species in the vapor at this temperature? So at this temperature, aluminium chloride will dimerize. So dimerization, it is a chemical process or a chemical reaction where 2 identical molecules combine to form the same one single molecule through dative bonding. So for inorganic chemistry, we use dimerization through the dative bonding, right? So aluminium, it is aluminium chloride. It is an electron deficient molecule, right? It hasn't reached the electronic stable noble gas electronic configuration. So we have 6 electrons in the outermost shell, right? So I want to illustrate using this diagram. So this is our aluminium, this is our chlorine, and then chlorine, and then you have a single bond here, single bond here, single bond here. So this aluminium is not fully occupied in the outer shell, right? So we need, as it sublimes, it will have there is dative bonding between this aluminium ion and the other aluminium chloride molecule, right? So we are going to have another aluminium chloride here. So we have another aluminium. So let me make the circle bigger. So this is aluminium, and then this is the chlorine, and then this the chlorine. So we have another electron here, electron, the bonding, right? So we can complete the outer shells for the chloride, the chlorine atoms, right? So chlorine has got 3 lone pairs of electrons. So this lone pair will be shared to this aluminum, right? And then this the lone pair on this atom will be shared again to this aluminum to complete the electronic configuration. So you need to know that electrons are being transferred from the chlorine atom from one aluminum chloride molecule to the aluminum atom in the next aluminum molecule, and then the other chlorine atom will donate electrons again to that central atom again. So here the chlorine atom provides electrons to this, and then this chlorine atom provides to this one. So this one is true, and then here we're having aluminum donating electrons to chlorine, which is false. Chlorine is the one which donates the electrons, and then here we are having it doesn't show any dimerization. You need to say it is false, and this one is false again. So our answer is equal to A. And then we are now moving on to number 6. So number 6 says which row is correct. So the shape of the hydronium ion, right? So we have oxygen as the central atom. So it's oxygen at the central atom, and then we are having this proton, and then this proton, and we are left with one lone pair of electrons. So this positive sign indicates that we are having a proton which is coming to the reaction with without any electron to share. So there is dative bonding here, right? So you should take note of that one. We are having a dative bond here, and then for the sulfur dichloride, we are having sulfur as the central atom, and then 2 chlorine atoms here. So sulfur is in group 6. We have used 2 electrons, so we are left with 4. So meaning to say we are going to have two lone pairs of electrons here, right? So 2 bonding pairs, 2 lone pairs. We are having a band-shaped or non-linear. So this one is false, this one is false, and we are left with A and B. And then 3 bonding pairs and 1 lone pair. We are having a pyramidal shape. So this one becomes correct. So our answer becomes B. So number 6. Our answer is equal to A, right? A, non-linear and pyramidal. So our answer is equal to A. So this one is non-linear, and then this one is pyramidal. And then we are now moving on to number 7. So number 7 says when an evacuated tube of volume 400 cubic centimeters is filled with gas at 300 Kelvin and 101 kilopascal, the mass of the tube increases by 0.65 grams. Assume the gas behaves as an ideal gas. What is the identity of the gas? So PV, for ideal gas we use PV is equal to nRT. And then we want to find the identity of the gas, assuming that this one is an ideal gas. So N is the number of moles, so we can derive the molecular mass from this N by using this formula. N is equal to mass over mR. So mR is the relative molecular mass. So we are going to say PV is equal to mass over mR multiplied by RT. So we want to make PV the subject of the formula. So we are going to say mR is equal to mass RT over PV, and then we're going to substitute. So our mass is equal to 0.65 multiplied by R, the gas constant, which is equal to 8.31 multiplied by temperature in Kelvin, which is equal to 300 Kelvin. And then we divide by P, the pressure in Pascal. So here we are given kilopascals. So we're going to say 101 multiplied by 10 to the power 3, which is equal to the kilo-thousand, right? Multiplied by volume in cubic meters. So we are given volume in cubic centimeters. So it's 400 multiplied by 10 to the power 6 to convert to cubic meters. So we're going to punch this straight direct to our calculator. So it's 0.65 multiplied by 8.31 multiplied by 300 over 101 multiplied by 10 to the power 3 multiplied by 400 multiplied by 10 to the power negative 6. So we are going to have mR being equal to 400.1100, right? So which is mR is approximately equal to 40. So we go straight to the periodic table where there is the mR 40. So the element is A, the argon, right? So number 7 is equal to A. And then we move on to number 8. So number 8 says nitrogen and carbon monoxide behaves, both have mR of 28. The boiling point of nitrogen is equal to 77 Kelvin, and the boiling point of carbon monoxide is equal to 82 Kelvin. What would be responsible for the difference in the boiling points? So carbon monoxide has got a higher melting point than nitrogen. Why? Because here we've got a permanent dipole moments within this molecule, oxygen being a more electronegative atom, which tends to draw the electrons towards itself and attain a partial negative charge, and then carbon attains a partial positive charge, and then there is electrostatic force of attraction between oppositely charged particles. And then here it is a non-polar molecule. The electronegativity of nitrogen cancels out because they are identical, so they've got the same ability to draw electrons towards themselves. So there is no dipole moments in this molecule. It is a non-polar molecule, so they are held by weak van der Waals forces. And then here we have permanent dipole moments. So that's the reason why carbon monoxide has got a higher melting point than nitrogen. So we're going to the options. So option A says carbon monoxide is a permanent dipole, and then nitrogen is a non-polar. So this is true. And then nitrogen is a sigma bond and a pi bond, and then carbon monoxide contains only a sigma bond. This is false. So the structure of carbon monoxide is this one, right? So in multiple bonds, one is sigma and the rest are pi bonds. So this is dative bond. So you should take note of the dot and cross for carbon monoxide. It shows dative bonding, electrons being donated by oxygen. And then we move on to option C. Nitrogen is a strong triple bond, whereas carbon is a double bond. Carbon monoxide is a carbon to oxygen double bond. False. Carbon to oxygen it is a triple bond with a dative bond. So this is false. And also boiling point is governed by intermolecular forces, not intramolecular forces. So these are intramolecular forces, whereas boiling points physical properties are mainly governed by the intermolecular forces within the lattice structure. And then we move on to number D. The carbon monoxide molecule has one more electron than the nitrogen molecule. So this is false. So our correct answer is equal to A. And then we move on to number 9. Which statement about enthalpy change is correct? The enthalpy change of reaction is always negative. So this is false. Enthalpy change can be either endothermic or exothermic, right? And then the enthalpy change of combustion is always positive. Enthalpy change of combustion is always negative. So this one becomes false. The enthalpy change of formation is always positive. This also becomes false. And then the enthalpy change of neutralization is always negative. So our answer is equal to D. And then we move on to number 10. Number 10 says, what is the definition of standard enthalpy change of neutralization? So standard enthalpy change of neutralization is defined as the energy evolved when 1 mole of water is being produced from an acid and an alkaline. So we are going to produce 1 mole of water. So that's where the whole definition lies, under standard conditions of 298 Kelvin and 1 atm of pressure. So the enthalpy change of reaction is when 1 mole of an acid, so it's 1 mole of water, so this becomes false. 1 mole of an aqueous alkaline, so this becomes false because we are referring to 1 mole of water. And then 1 mole of acid, false again. And then when an aqueous acid and an aqueous react together to produce 1 mole of water, so our answer is equal to D. And we are now moving on to number 11.